today we're gonna have our ninth session in turbomachinery flows, and as I said, starting from today, we're gonna see some other stuff in turbomachinery related to the measurements and some related stuff to analysis, computational analysis in turbomachinery as well. First, we're gonna start with the turbulence, and we're gonna see what is the turbulence and unsteadiness in a turbo machine. So you might know that turbulence is something that is an irregular motion with fluctuation. So when you actually measure the flow, turbulence shows up itself as some fluctuations in velocity. Uh, the turbulent flow is inherently unsteady. So actually, the thing you have to note that is the difference between unsteadiness and turbulence. Turbulent flow is unsteady itself, but this unsteadiness does not have some does have some other forms rather than only being chaotic. So we will see it in a moment. So what we have in here, if I can draw something, let's see. For example, if you have your velocity measuring in y-axis and in x-axis, let's say you have uh, time and you're measuring at some point your velocity inside the flow, whatever flow it is, when you're measuring it, as we said, you're seeing some fluctuations in velocity. So something like this could be a representation of your velocity and the fluctuations of your velocity. The turbulent fluid motion can be considered as an irregular condition of flow in which you have various quantities, like one is the velocity that we are showing in here. It could be also your pressure, so it doesn't matter. You have pressure or velocity or whatever else that you are measuring it, and it shows as you see in here a random variation with time. So also it could be a random variation in space, but right now we are considering only time, and in such a way that you have some statistical average of these quantities, and you can quantitatively express these, let's say, statistical averages. What we have in here, let's say this horizontal line is our average. So what you are measuring was your, for example, u velocity. So you're measuring u velocity. So for example, at this moment of time in here, you're measuring the velocity, and you see that your velocity is this much. This is your, let's say, velocity in here. This is your u velocity at this time, and this time could be t equal to t1. So what is the deviation of this velocity from its mean value? So we call the mean value by, we show it by u bar, and this is the deviation of your velocity from the mean value that you call it as u prime. So in this case, you can say that your u is equal to u prime, u bar plus u prime. So your u is actually your instantaneous velocity. Your u bar, as we said, is your mean or uh, averaged velocity. It's average velocity, and this u prime we call it the fluctuation. So this is the fluctuation that you have. And actually, it's postulated that the fluctuations inherently come from disturbances. And these disturbances can come from roughness of a solid surface or anything, and they may be either dampened out due to viscous damping or may grow by drawing some energy from the free stream. So it apparently can be damped or may grow. And at the Reynolds numbers less than the critical Reynolds numbers, you're familiar already with the critical Reynolds number, the kinetic energy of flow is not enough to sustain the random fluctuations against the viscous damping. And in such cases, you have laminar flow continuing to exist. And at somewhat higher Reynolds number, uh, which is higher than the critical Reynolds number, the kinetic energy of the flow will support the growth of these fluctuations, and consequently, you have transition from laminar to turbulence. And the most important characteristic of turbulent motion is the fact that velocity and also pressure at some point fluctuate with time in a random manner, as we show it in here to you. So if I want to show it in a proper way, let's say this way, you remember that there was this experiment in Reynolds laboratory back in 18th century, late 18th century, and he conducted experiments with pipe flow and by feeding into the stream a thin thread of liquid dye. So this is a dye, liquid dye with other different color. And for low Reynolds numbers, the dye traced a straight line, like in here. This was a straight line, and it didn't disperse. And with increasing the velocity of the water inside, the dye, the dye thread got mixed in all directions, and the flowing fluid appeared to be uniformly colored in downstream flow. So it started to mix, and then you will have a uniform color. And Reynolds inferred that on the main motion in the direction of the pipe axis, so in this direction, the x-axis, there exists a superimposed motion. Okay, this is very important for us because this superimposition will lead us to use the decomposition that we just mentioned it there. So he inferred that there is this superimposed motion in x direction all along the main motion at right angles to it. So this superimposing is at the right angle. So if it is in the main flow is in x direction, you have the y and z direction normal to it. So you have this superimposition in those directions. This superimposed motion will cause the exchange of momentum in transverse direction, and the velocity distribution over the cross section is more uniform than in laminar flow. That's why you remember in your fluid mechanics that if there is a profile of laminar flow, the fully developed flow like this, for a turbulent motion, the velocity distribution is more uniform, so you will ended up with a much uniform, let's say, turbulent profile. And this description of turbulent flow, which consists of superimposed streaming and fluctuating, or sometimes this fluctuating, we are calling this as eddying motion. Uh, what is eddying motion? It comes from these eddies. What are the eddies? Eddies are bulk of the fluid. So you are seeing some sort of coherent structures in fluid, and you call these as eddies. And we know this is superimposition. What is the superimposition? U is equal to U plus U prime. This is the decomposition, or and we know it as the Reynolds decomposition of turbulent flow. So I guess you already remember these from your um fluid mechanics and aerodynamics courses, but this is very important for us to see the Reynolds decomposition at first in here, and then we will have a trickle decomposition in turbomachinery in next slides. And based on this, actually, um, what you ended up with was the Navier-Stokes equation. So what was the Navier-Stokes equation? We said that we have some governing equations, and these governing equations for your instantaneous velocity. See, this is your um, instantaneous velocity. So you have u in here. So the governing equation for instantaneous velocity is the Navier-Stokes equation. As you know, the Navier-Stokes equation is governing velocity for any fluid flow. But you do also remember that sometimes when you are engaged with modeling of these equations, you had to make some um, simplifications. So what are those simplifications? Those simplifications are coming from the, um, as I said, so-called Reynolds decomposition. So again, please keep in mind that these Navier-Stokes equations are there just to give you the values of instantaneous velocities like u, v, w in x, y, z coordinate system, and also instantaneous pressure values at each point and as I said, at each instant of time, because we said that this is instantaneous equation. And then uh, you have in a tensorial form. What is the tensorial form? This is pretty important for you to be able to write this Navier-Stokes equation in tensorial form. As in this slide, this previous slide, as you can see, the Navier-Stokes equation are three momentum equations and one continuity equation. So these are not written in tensorial form. The tensorial form is this form. So this form is much simpler, right? We just wrote three lines of momentum uh, equations in one line. This is one line. So what does it mean? We are using tensors I and j in here. This is called a tensorial form or Einstein notation. Okay. So instead of I and j, you can put 1, 2, and 3, and then when you just put 1, 2, and 3, you will end up with the so-called three momentum equations. And the continuum equation is there. So the continuum equation in tensorial form, if I remember, it is exactly duj dx dxj is equal to 0, and j is equal to 1, 2, 3. So if you put j equal to 1, du1, u1 means your u velocity, u2 means your v velocity, u3 means your w velocity, and correspondingly your x1 is x direction, x2 is y direction, x3 is z direction. This is just an explanation of how to write the tensorial form. The tensorial form for continuity, we said, is this one. Why? When you write with I and J, and when you have repetition of some, let's say, um indices, like in here, let me write it again. I just wrote duj over dxj. J is not important. J could be alpha, beta, whatever you're using as index, you are using it. When you have repetition of index like this, so you have j repeated, the tensorial form or Einstein notation suggests that you have to use summation. It means that you have to sum up over j's. And we said j is from 1 to 3. It means that you have to write du1 over dx1. u1, we said u, so it is du over dx plus, because we have to use summation because of this repetition. Then the second, which is v over y, and the third, which is w over z. It is equal to 0. What is this? It's exactly your continuity equation. So you have to be familiar with this notation in Navier-Stokes as well in order to make it simplified. So when we write it in tensorial form, I guess there is no questions so far, right? Do you need any more explanation on the tensorial form? It's so easy. You just need to remember that whenever you have repetition, for example, in here, see, can you see my pen in here? Okay, no one can see it. Uh, See, there is this repetition in here. Okay, I and I. It means that it has to be summed up over I index. So when you write it down, you have to write it down like this. U1, which is U, D what? Uj. Duj. J is starting again from 1 to 3. So for example, if you started from 1, you will write du1, which is du over dx plus. Now we are summing up over I, so it is again v, but j still is 1 in here. So v du dy plus w du dz, right? This is like this. This is summed up over I only. And then you have to include j as well. But the important thing is that you have to use Reynolds decomposition to be able to model your turbulent flow. Actually, the first thing that you are engaged in modeling of turbulent flow is to use the Reynolds decomposition to come up with such terms, such, let's say, equations. And these equations, as you can see, these are written in mean values. So all of them are, let's say, written in uh, mean values. U, V, W, all of them are mean W's, mean values, U, V, W, and P mean. In CFD, computational fluid dynamics, we model these actually we use this modeling. So why we are using this modeling? Because if you just put this Reynolds decomposition inside the Navier-Stokes and write the whole Navier-Stokes, you will end up with some additional terms. What are these additional terms? These additional terms are, let's say, double. How can I say it? They are including the multiplication of two variables. For example, they are including u prime and v prime average, or even u prime average. These additional terms need to be modeled. And if you cannot model these additional terms, because these are not something that you can put directly the values inside a mean flow that you are doing uh, analysis on right now, you are getting the mean flow, let's say, behavior. But these are not something that you are getting from the mean flow. These are multiplication of, for example, two velocities and then get averaged, two fluctuations of velocities and then get averaged. That's why uh, you cannot model these. You cannot use these as a, let's say, direct information from the flow, but you have to model these. So the modeling these stuff is the whole CFD that we are dealing with nowadays. We were talking about the turbulence. We said the turbulence is irregular flow. It is inherently unsteady. But let's look at the uh, unsteadiness of flow inside a turbo machine. You know that turbo machine is, for example, an axial compressor or is an axial turbine or whatever. Whatever it is rotating, right? So when it is rotating, it starts from somewhere. So when one blade tip is at this point, after one revolution, you will have this tip at the same point. And after two revolutions, you will see it at this very first point. So it means that it is following a sinusoidal wave, right? And this sinusoidal wave in turbomachinery makes the flow unsteady for us. Because the flow is not just uh, uh, behaving like a normal chaotic turbulent flow. It is repeating itself as well. When it is repeating itself, uh, you can fit a sinusoidal wave to this repetition. And this sinusoidal wave has some characteristics which are known to you. For example, the amplitude of this sinusoidal wave is known to you, right? The period of this sinusoidal wave is known to you. This is a period. The wavelength is known to you. So if it is in a space instead of time, I put a space. This is also be the wavelength of this sinusoidal wave. So there are some deterministic, let's say, uh, values that are apparent that you apparently know them in these sinusoidal waves. How do we just show the turbulence over it? For example, if you are measuring just the u velocity, just uh, one component of velocity through time, how you are measuring it? You have, for example, turbo machine, right? Your turbo machine, and this is the side view of this turbo machine. The flow comes, and then this is rotating, and the flow goes away from this turbo machine. Suppose that you are putting some device in here, and this device can measure the u velocity for you. Okay, so this is you standing and holding this device, and you're measuring uh, the u velocity like this. What you're seeing is not a fully sinusoidal wave, but some fluctuations also exist over this sinusoidal wave. The same we did with this uh, irregular and chaotic turbulent flow. You can do it with this. So at any point, for example, if you have, let's say this point, at any point, you have your u velocity, which is your instantaneous velocity. The velocity that at that instant of time, what is the time instant? This is t1. At t1 equal to some seconds, you are measuring with this device, you're measuring your velocity, and this is that velocity. But also, we said that you kind of have some um, turbulent fluctuation, which is we called it before as u prime. And now we are seeing that, okay, these fluctuations, u primes, are following a sinusoidal wave. And the sinusoidal wave kind of uh, give us the, I mean, these fluctuations are uh, fluctuating about this mean value. The mean value is not right now this horizontal line. The mean value is the sinusoidal wave. So the sinusoidal wave itself is mean value. So what is the mean value of this mean value? I mean, the mean of sinusoidal is this one that we are showing by u tilde. This is u bar, and this we call it as u tilde. So based on this, can I write it like my instantaneous value, first of all, is my mean value plus some fluctuation. And I said that my mean value is also composed of another mean, right? Plus another fluctuation. And u double prime, this u double prime is actually what we call it as uh, deterministic fluctuation. Why I call it as deterministic? Because we can somehow determine the changes as it follows a certain period or frequency. As I said, this is its period. From here to here is one period. So when you can fit it into a sinusoidal wave, it means that it has a certain period, it has a certain frequency, it has a certain amplitude, blah, 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 blah. That was the uh, actually, that's why we call it deterministic. It's not non-deterministic. You can determine these values. So overall, what you can write is that your instantaneous velocity is your u tilde plus u prime plus u double prime. So what is u tilde? You remember u tilde was the average of the average. So average of the average flow, average of the sinusoidal wave will give you a completely horizontal value. So this is better shown in here. So we said that because we have some non-linearity, we have extra unsteady stress terms. And these extra unsteady terms will be generated in flow equations when you do the time averaging. So you do the time averaging over u prime and you are getting u tilde. These stress terms are similar to the Reynolds stress terms that are generated by turbulence, but in the cases of interested, they are generated by periodic unsteadiness in turbomachinery. And we said that these periodic unsteadiness, they have a distinctive frequency, and that's why we call them as deterministic stresses or deterministic fluctuations. So in these two graphs, you're kind of comparing normal, let's say, turbulent flow that has the fluctuations u prime, and you have unsteady turbulent flow, which happens in turbomachinery. So in the unsteady turbulent flow, the mean u bar, which is your mean velocity, has also another mean value, which is this one, and you call it as u tilde. So that's how you ended up with the triple decomposition. We said that in previous slide we showed that u is your u tilde plus u prime plus u double prime. So if you have a phi is anything. Phi could be your u, v, w, or p. You can show your phi is equal to phi bar, which is your might be your tilde, and you have prime and double primes. So let me check. Okay, because of distinct values in here, we call it as triple decomposition. So before we had Reynolds decomposition, or the Reynolds decomposition was easy. It was, let's say, u is equal to u bar plus u prime. So it has two components. But in here we have three components, and we call it as triple decomposition.